In Chapter 10, we'll be discussing radical expressions. And so the first type of radical expression we'll look at are square roots, and then we'll discuss other types of roots, and then we'll start working with them and doing operations with them throughout the chapter. So first we'll start with something familiar, square roots, and their related term. A square root is one of a number's two equal factors, and we've talked about that before. So the square root of 25 is 5 because 5 times 5 gives you 25. Here's the sign that we use. It's called a radical sign. And the radicand is the number that's under the radical sign. So if we did put a 25 under here, that would be called our radicand. So looking here, the square root of 9 has actually two values. We usually think of just 3 because 3 times 3 is 9. But negative 3 is also one of our options because negative 3 times negative 3 is 9. So each square root has two values, the positive and the negative. So when we see something here, it says to avoid confusion, we use the radical sign to indicate a positive square root called the principal root. So when you just see this right here, the square root of 9, it's just referring to the principal root or the one that's positive. So when we see the square root of 9 like this, we would just write 3. And if we wanted the negative one, we would actually put the negative out in front of the square root sign or the radical sign. So this answer here would be negative 3. And so we have a couple examples here. We're just looking for the square root of 4. This first one is just the principal root, which means we want the positive one. So we think what times itself gives me 4, and that would be 2. And we just put 2, we do not put negative 2, we just want the principal root. But over in this next example, it has the negative out front. So this is going to be negative, and we think what times itself equals 16, and that's 4. So negative 4 is that one. We won't just be looking at square roots, we'll be looking at other types of roots. To indicate roots other than square roots, an index is added to the radical sign. So here we have a radical sign, but there's going to be a little number up here. Right now it's an n because we can put any number, and we'll just be working with whole numbers right now. So you might see a cubed root, which would look like this. It's one of a number's 3 equal factors. So you're thinking what multiplied times itself 3 times would give you the radicand, the part that would be under the radical sign. And then really we can put any number there. We could have a 4 or a 5 or a 6. So looking right here, it says if, or maybe we could even say since 2 cubed is 8, we know the cubed root of 8 is 2 because this is asking what times itself 3 times will give me 8, and we know that's 2 times 2 times 2. So looking at these couple examples, we have 125. And so we're thinking what times itself 3 times would give me 125. There's a couple different ways to think through this. You should start getting familiar with some of your cubed roots. We could start with 2 and think, well, 2 times 2 times 2. We could start with 2 and think 2 times 2 times 2. We know that's 2 times 2 is 4, times 2 is 8. And we could keep working our way up. 8 is a long way from 125. But when we look at 125, we see it ends in a 5. The only way something can end in a 5 is if one of its factors is 5. So we should try 5. And so I think this is 5. And the way we can check is we'll go back and think, okay, 5 times 5 times 5. I know 5 times 5 is 25 times 5, and 25 times 5 is in fact 125. Please notice here, once I took the cubed root, it's just equal to 5. Do not put the cubed root as 5 as your answer. That is not correct, so the answer is just 5. The next one is the 4th root of 81, and we want to think what multiplied by itself 4 times will give me 81. So it's an odd number, so we definitely won't try any even numbers because an even times an even times an even times an even is always even. So we're going to try odd numbers. And so we could try the first odd number besides 1, So I think this is 3. So I'm going to try it out. And I don't have to multiply right across. The easiest way is probably think 3 times 3 is 9 times, and then another 3 times 3 is 9, and we know 9 times 9 is 81. So the answer to this is 3. So those are other roots besides square roots. So in those last couple examples, we got integers as our answers, or rational numbers. But many radicals are irrational numbers. In fact, most of them are. So an irrational number is a non-repeating, non-terminating decimal, is what it would look like in decimal form. To approximate the square root, that's an irrational number. You just try to think what it's bound by. So we're going to look at these next couple examples to show us how to work through these things that end up being irrational numbers. So what two integers are the radicals between? So here we have the square root of 7. Well, we know that the square root of 4 is 2, and we know the square root of 9 is 3. So the square root of 7 would fall somewhere between there. So we think of our perfect squares. We can list them here. Please make sure you're familiar with these. Actually, I didn't put one here. I should have put 1, because 1 times 1 is 1. And so if we know these, we can figure this first one out pretty easily. We see 7 falls between 4 and 9. So therefore, the answer to this, what two integers are the radicals between? Well, it's between 2 and 3. So the square root of 7 is going to be 2 point something. Looking at the next one, we have the square root of 129. That's a larger number. If we keep continuing our pattern down here at the bottom, we have 100 was 10 times 10. 11 times 11 is 121. 12 times 12 is 144. And so we see 129 falls in here. So we know the square root of 129 is between 11 and 12, because the square root of 121 is 11 and the square root of 144 is 12. So the square root of 129 is somewhere between 11 and 12, 11 point something. This last one here is not a square root, it's a cubed root. So we want to find the numbers that the cubed root of 50 is between. So now we're going to have to look at perfect cubes. And so it is good to know the first several of these also. So our perfect cubes, 1 cubed is 1, 2 cubed, 2 times 2 times 2 is 8, 3 cubed, 3 times 3 is 9, times another 3 is 27, 4 cubed, 4 times 4 is 16, times another 4 is 64, 5 cubed we saw before is 125, and 6 cubed I'll put in there, that's 216. You really should be familiar with the first 5 or 6 of perfect cubes too. So looking at these, we see that the cubed root of 50 falls between 27 and 64. 27 is 3 cubed and 64 is 4 cubed, so we know that the cubed root of 50 is somewhere between 3 and 4. We're going to do a little investigation here just to see a relationship, a very important relationship that we have in algebra. So we have the square root of 4 times the square root of 4. We could look at that a couple different ways. Square roots, when we deal with order of operations, will end up falling into exponents. But we can even think of this is grouped together, so this is like parentheses. So the square root of 4 is 2, times the square root of 4 is 2, which 2 times 2 is 4. Over here, we learn with our rules of exponents that if we have the same base, we can add the exponents. So we have 4, 1/2 plus 1/2 is 1, which is just 4. Well, this problem gave us 4 as an answer, and this problem gave us 4 as an answer. And so we can know that the result here, the square root of 4, is really the same thing as 4 to the 1/2. Which is a really important relationship to know, and we're going to work with that a bit through this chapter. A pretty easy way to see we convert this. starting with our 4 to the 1/2, well, we see that's under our radical. This 1 here is actually the exponent of 4. So this is like 4 to the 1st. And then the denominator is the index right here. Now, we don't write the 2 normally if it's a square root. It's an understood 2, but you can write it. And so we see that the denominator is the index and the numerator is the exponent of 4. So here's a way we can convert between radicals and exponents. If you have a number to an exponent that's a fraction a over b, we see that the b becomes the index and the a is the exponent. Here's a couple examples. Change each exponential to radical form. From that rule above, we see that this is going to be equal to, we're going to have a radical. Our 3 is going to be the index, and then 5 squared, 5 goes under the radical, and then 2 is the exponent. So we can rewrite this as the cubed root, and 5 squared is 25. Our next one has 2 factors. In order to write this as a single radical, we have to have a common denominator. So we can write our index in. This one would have an index of 2, and this one would have an index of 4. So what we're going to do, first we're going to rewrite this so they have a common denominator. So 1/2 is same as 5 to the 2/4, and then we still have our x to the 3/4. And so what we have here, a radical sign. The index is going to be 4 because of the denominator, and then we're going to have a 5, and we'll have a squared because the numerator is 2, and then x cubed. And we can simplify this because so we have the 4th root of 5 squared, which is 25 x cubed. So we rewrote exponential into radical form. And now this last set of examples, we're going to start with radical form and change it back to exponential form. So we're going to be working in this direction. So we have the 5th root of 3. Well, in order to write this, we're going to have a 3, and we're going to have a fraction here, and we know the 5 is going to be the denominator, the index is the denominator, and we have to figure out what the numerator is here. Well, 3, this is really just 3 to the 1st, so we're going to have 3 to the 1/5 power. This next one, we can write each of these individually. So similar to our first one here, this was a 3 to the 1st. Here we're going to have a 7 to the 1st. So if there's not an exponent written, it's really just to the 1st power. And so we're going to have a 7, an x, and a y. And each of these are going to have 4s in their denominator of the exponent because of the index out here. And then 7 to the 1/4 because the exponent was 1, x to the 3/4 because the exponent was 3, and y to the 2/4. We have to simplify here because we don't want to leave things as unreduced fractions. So we have 7 to the 1/4. 1/4 can't be reduced. 3/4 can't be reduced, but 2/4 here can be reduced, and we reduce that to 1/2. So this is y to the 1/2. And so that's our introduction to radicals, and then also realizing that we can change from radical form to exponential form using this relationship here. The denominator becomes the index of the radical, and the numerator is the exponent of the radicand.